Now moving on the schedule, we have our next oral communication that is going to be presented by Matheus Pereira, who is currently a PhD student, right, at the graduate program of physics of Federal University Fluminense. Matheus today is going to talk to us about quantum system analog model for a particle in a black hole background. Please, Matheus.
Thank you. Hello, everyone. My name is Matheus, and I am a doctorate student of physics at Universidade Federal Fluminense. And today I will talk about an analog model for a particle in a black hole background. Before I start, I'd like to give a special thanks to CNPq for funding this research, and to Professor Crispino and to the organizing committee for inviting me. So, why it is interesting to study an analog model, and what are analog models? Well, some physical systems are naturally inaccessible to us due to large scales, huge energies, etc. However, there are systems here on Earth that can mimic the properties of those inaccessible systems, and those are called analog models. So, for example, the magnetic monopole has never been observed in nature, but there are systems that we can build today that can manifest properties of the magnetic monopole, such as spin-line systems, position-dependent mass quantum systems, Bose-Einstein condensates, etc. So in our case, we are dealing with a black hole. So for the black hole, we use another approach. In this case, the first thing we need to do to build an analog model for a scalar particle in the background of a Kerr-de black hole is to tackle its dynamics. We will need the angular and radial solutions of the wave equation. And in parallel to that, we will investigate the dynamics of a particle constrained to move on a curved surface. In our case, it will be a spheroidal surface. And then we will connect both problems, thus creating an analog model. All of this is based on a paper me and my advisor published last year in Annals of Physics. And so, for start, the Kerr-de line element can be seen here. We have a few functions, a function of r, a function of theta. These three lines here, this is xi or xi, it is a constant. Lambda is the cosmological constant, and a is related to the angular momentum of the Kerr black hole. Now, since we are in the vicinities of a black hole, we are dealing with a relativistic wave equation, so we will need the Klein-Gordon equation. And once we separate the Klein-Gordon equation using simple separation of variables, we will get a radial equation, like equation 1, and an angular equation, like equation 2. We notice here that we have those functions d and delta theta in the denominator of those equations. That means singularities. And if we solve the angular equation first, we can introduce a change of variables, like x equals cosine square of theta, and then we will get something like equation 3. And here we see three singularities in the middle term, in 0, 1, and AH. AH is a constant. And then we already have some ideas as what the solution will be. So to really find the solution, we can use a F homotopic transformation, like equation 4, and then whichever value of A, B, and C we choose, we will get a Hahn differential equation. So This is a very well-known equation, and we can already solve that angular Klein-Gordon equation using local Hoyne functions. And then we can use a similar approach to solve the radial equation. The only difference will be the change of variables here. We needed to define a new radial variable because of singularities. But it is the same function, different coefficients. Now, it is important to note here that we have a lot of singularities in the radial domain. If we tackle the radial equation head on, we will end up in the blue region because it is a power series. So we need to augment the domain of our solutions. Once we do that, we end up in the yellow region, which is the physical acceptable region. Okay, so this was the particle in the background of a de Sitter black hole. Now, for the particle on an oblate spheroid, we can use the thin layer method. When we use the thin layer method, we end up with something called the geometric potential. The geometric potential, you can see here, is defined like so. It is a function of the mean and Gaussian curvatures of the curved surface we need. It is important to note that those curved surfaces, they are feasible in a lab. So someone somewhere here on Earth can build such a surface. Now, an oblate spheroid needs the oblate spheroidal coordinates you can see here, and then using this and the geometric potential, we get the Schrödinger equation and the geometric potential. Now, the geometric potential may look scary because it has a 3 here in the denominator, but we can solve this. And to do that, we use separation of variables once again, another change of variables, another F homotopic transformation, and then we end up with equation 14. And then we think, well, this is Hoyne's equations. It's not. This is Schoeffer's differential equation. Schoeffer's differential equation is an equation with 4 singularities, but the difference between this one and Hoyne's is that the singularity at infinity is no longer regular, and you can see why. It's because of this alpha in the middle term. So the only hope we have is to use the definition. Let's use a power series. This is the definition of Schoeffer's eta function. And if we use a power series, we get this. This is the solution for the free particle on an oblate spheroid. Now, this is not Hoyne's. This is not a Hoyne special function. So how can we transform this into the same problem as the particle in the background of a de Sitter black hole? Well, this is the domain. In our case, we are in the blue region. And these are the plots of the probability densities for the first few eigenenergies. The blue one is the least energetic, and the red one is the most energetic. Here, we plotted the first few from 0 to 3. So to actually transform our problem into the problem of a particle in the background of a black hole, we use this very specific F homotopic transformation and this huge external potential. The difficulty is to find these constants u0 to u4, but we can't do that. And then the resulting equation will be, once again, the general Hoyne differential equation, and we will get our analog model. So for my final remarks, we found the eigenenergies and eigenfunctions of the black hole problem using Hoyne's functions. We found the eigenenergies and eigenfunctions of the spheroidal problem using Schottky's eta functions. And once we applied an external field, we did create an analog model for the particle in the background of a KRDC, the black hole. So thank you.
Thank you, Matheus. I think we have time for 1 or 2 questions. Marco.
So thank you for your presentation. So you have talked about the thin layer method. Is that correct? So we have said that this method is interesting because the curved surface, they are feasible in lab. So I was thinking about when we talk about your analog model, do you have any insights in what conditions or situations that your model would be feasible in lab?
So we found a group in Japan who can build some interesting surfaces, and they did a huge review. So we believe that it is possible to really do this. In this paper, we didn't actually calculate the numbers that we would need, like the dimensions of the. We didn't do that, but we could have done that. We just didn't do. And we have a future paper that we have some numbers there. It is related to a string theory black hole, so we have huge numbers. But in this case we didn't have the numbers, but we could have. This A is related to the it is the location of the foci of this spheroid, so it is a physical number. We could have done that.
So so it's actually possible to, in some sense, construct this.
Yeah.
Okay.
These guys here, Rich and Hansen.
Okay.
Those guys.
Okay, nice. So
They
thank
can
you.
do it.
Thank you. Thank you very much.
Any further question? Well.
So we were trying to find online the Schottky function. So what is it really? Actually, we couldn't find online. Okay, thank you.
Well, let's thanks Matheus again.